Good morning, everyone, and welcome to another Athena talk on Energetic Mediterranean University Sci Cafe talk. It is our great pleasure and honor to have today with us a very distinguished speaker from Spain. His name is Stephan Roche. I hope I pronounce your name correctly. And he's an ICREA professor. He's working in the Catalan Institute of Nanoscience and Nanotechnology. And he leads a theoretical and computational nanoscience group with focus on materials, innovative layered materials like graphene and topological insulators. He studied theoretical physics at ENS and he got a PhD at Grenoble University in France. And he also worked in several innovative countries like Japan, Spain, and Germany. And he was first elected as an assistant professor in 2020 and then joined the ICREA in 2009. He has received several distinguished fellowships, such as Friedrich Wilhelm Bessel Prize and Alexander von Humboldt Foundation Prize. And he was also a member and one of the leaders in Graphene Flagship. He was leading the work package of Spintronics, and he was also a division leader in Graphene Flagship. And now he's a coordinator of quantum communication activities at his department. So we are very glad to have Stephan today with us. And the topic Stephan will discuss with us is artificial intelligence for boosting the design and engineering of innovative advanced materials. So once again, we are very glad, Stephan, to have you. And please, you have 40 minutes for your presentation and then approximately 10 to 15 minutes for a fruitful Q&A, I believe. Thank you very much.
Thanks, Sto. Kalimera, everybody. Thank you for this kind invitation to share with you my perspective on the use of artificial intelligence for innovation in advanced materials. So what I like to say first is that so I'm working in an institute truly engaged into exploring the potential of nanomaterials at large. So we are really like molecules, nanotubes, and so on, 2D materials. And we try to use these materials for application in energy, like including photovoltaics or batteries or quantum application and so on. But we since like about 2 or 3 years, we have realized that artificial intelligence will be a game changer in innovation and impact. So we have set up a platform, we have hired some specialists, and we are most of the groups are actually closely connected with new research in which we are trying to harvest what AI can do today for materials production or material characterization, material design. And I think this tendency is becoming very strong. Manos mentioned the IMI partnership and the IM4U program in the European, launched by the European Commission. So there will be quite a lot of funding for this year and the next 2 more years, but beyond that also. And AI is likely to become a key ingredient of any project that will be submitted in this course. So that said, I would like to say that there are three different research directions in which our institute is more strongly focused, let's say. One, it is to develop using advanced materials, novel kind of implants, brain implants, and to interface computers with a human brain somehow. So it's a very exciting research line. Then we are also strongly using these STEM equipments in order to build what we call digital models or digital twins of materials as grown. And that's very important. And this uses massively pattern recognition, deep learning techniques, or artificial intelligence. And these digital twins are very interesting because then we can explore their property in the digital space. And we can even envision to play on this digital twin, apply strain, changing temperature, changing the composition, and so somehow predict what the real material or the real materials will behave under those conditions. And that can allow to think about reverse engineering. And that's really something I think innovative that can eventually enter into pilot lines and so on. So very exciting to work on this. My group is indeed more about simulation, and as you will see, I will illustrate a couple of activities that we have developed over the past years. Let's say that we are also developing kind of unique techniques in order to compute physical properties. There could be optical, dielectric, magnetic transport of gigantic models, and we can say that with this methodology, we could reach the trillion atoms frontiers, which is really, really big. And that AI technique, like machine learning, also allow to design very realistic models. So we can go to highly predictive modeling, almost DFT or ab initio accuracy with models having billions of atoms and completely in a situation or in a distribution which is absolutely not ordered. They can have interface, disorder, roughness, and so on and so forth. So that's kind of a revolution for material design, and these kind of tools will probably spread through all sectors in the few years to come. So, I mean, you are aware. I mean, Manos mentioned. I think Manos mentioned DeepSeek, the Chinese discovery, which has made the American quite unhappy, right? Nvidia and OpenAI and so on. But definitely, if you've been in sorry, in China, if you've been in China recently, you will see how artificial intelligence is massively introduced at all levels of the society. Is just unbelievable. I was just in November last year, and I could speak for an hour about all the crazy things I've seen in China now. Anyway, so there is a big impact on our civilization and society, but at the same time, our technologies, which are supporting, let's say, all the electronic semiconducting, are strongly dependent on a high energy resource. Okay, which is even further accelerated by the development of hardware specific to train AI models. Right, so that's a real big problem, basically because all electronics is related to the flow of charge, which by joule dissipation generate heat. So we are losing energy in all electronics, mobile phone, computers, and so on. And actually, the development of AI hardware is accelerating the massive production of what we call electronic waste. So there is an estimation of several millions of tons, additional tons of waste that will be produced during a decade because of this new hardware that are coming. So that's really a problem. Okay, there is no solution that can come from the alliance of giants in semiconducting industry because, as it say here, despite the advance they can make in the few years to come, they increase the performance, but for the same power. They do not reduce the power. They just need more and more performance because we need more and more information, data storage, and information processing, gigantic database and so on. So there is no gain from the improvement of the technologies. So we will not save any money here. And the problem is that even if you just think about data warehouse where you have all this information for Facebook, LinkedIn, and all this Amazon and stuff, they will need in a few years from now almost a nuclear plant in order to operate their data center, just a single data center. So the waste of energy is just massive. It's just incredible. And if you want to train ChatGPT, for instance, you need 1,000 million watts. That's enormous. So not everybody will be able to have its own infrastructure and train new large language models in order to use them for accelerating innovation. So we will rely either on the NVIDIA infrastructure in the US or Chinese infrastructure, or maybe we will have some European infrastructure sooner or later. But the cost of energy will always be a big problem. And even, I mean, I didn't think ever that I would cite Donald Trump in one of my presentation, but eventually it happened. And as you know, probably they've signed the so-called Stargate project, in which, in the words of Trump, they really have to produce a lot of electricity. So they are conscious of the potential problem that is coming, and this is a general concern. Now, for Manos, my friend, please look at the screen. This is just for you, Manos, and create all his laboratory advances on solar panels. Of course, that would be a solution. If we could get a lot of energy from the sun, we will maybe have a possibility to solve this problem. That's a question mark, right? At the moment, we can produce electricity for housing and so on and so forth. And for computing, it's a bit more complicated. It's already difficult to have a completely autonomous laptop that you could bring in the mountain and work for days over there. That's kind of difficult. I don't know if Manos is working on this. That is quite challenging. But you can imagine that if you want to provide millions of watt hours, I mean, that would be very difficult. We will probably need a panel solar in the size of the galaxy, right? If we do the math. So we have a problem. We have a problem, and even the future of artificial intelligence is in jeopardy if there is no advances or progress in the hardware and the saving of energy costs, right? So there are plenty of questions in the current semiconducting technology in order to improve. One of them is related to the interconnect technology, because the interconnect technology is the components that drive the currents in your phones, wherever. And it turns out that more or less in a microprocessor, 50% of the energy that is consumed is evaporate in the air. Heat is heating the component and so on. So that's a lot, 50%, right? And in order to improve, to reduce the heat dissipation, there are not much possibilities, because the copper wires, people don't want to replace the copper in the interconnect. So the only possibility is try to work on the environment of these metallic wires. And a possibility is to try to improve what we call the delay time for signal propagation, which is proportional to the resistance of the copper wire times the capacitance, the surrounding capacitance. And if you want to reduce this time and so save energy, you are searching for a materials which is today it's a so-called organosilicate, but you will have a material which has much lower dielectric constant and that can also survive to the high temperature treatment and so on and so forth. So for years, for decades, semiconducting industries have been searching for such a material. And just like 5 years ago, people realized that they were growing boron nitride, but they realized that growing boron nitride at much lower temperature will result in a material which is highly disordered, okay? And by measuring the properties in the context of interconnect technologies, they were bingo, they had a materials that seems to really fulfill all the requirements. In particular, this dielectric constant was below 2, and all the other property was seemingly in agreement with what was sought after in the technology. So this work was made by Samsung and other groups in Korea, and I had the chance to be engaged into a collaboration with them. But we quickly realized that the problem is that if you want to really understand these highly complex materials, which are very disordered, you cannot avoid to use artificial intelligence. There is no way you can understand all the atoms will arrange one with respect to another if you don't have extremely accurate DFT-driven matching learning interatomic potential. No way you can. So we did this work, we started to do this work to work on this. We developed this matching learning potential that can then allow us to really use molecular dynamics and to construct to see how the structure will grow and then what will be its properties. So we can check this, and let's validation of this model was made by just a simple boron nitride flake or multiflakes in which you press with STM or AFM tip, and then you measure the how can I say, the Young modulus, the mechanical property. And basically, if you are using a kind of classical interatomic potential, you get something which is 200 gigapascal out of the experimental value, whether this AI, derived mechanical property fits into the range. So once you have the kind of certainty that your AI model has been well trained, then you can start to look at all the properties, right? And one particular property that is impossible to guess, to have an educated guess on that, was to find that in presence of a little amount of carbon or hydrogen, the thermal stability actually could improve in a certain range. So improve up to a 500 degree, which is huge. So that was improving metric of the materials due to the additional incorporation of additional atomic entities. We also worked on the fact that we want this kind of material surrounding the copper to be very resilient to the electromigration of the metallic atoms. So we studied the barrier property, and we found also, depending on the morphology of the amorphous boron nitride, the barrier will be highly permissive or not. And actually, our simulation have been matched with the experimental result very quantitatively. So this is an illustration that only artificial intelligence technique can provide you the parameters with which you can make predictive result that can guide the technology and the further optimization of the material. So it turns out that this type of prediction have been valued by the Samsung, with which we had a contract, and at the end of the day, we even filed a patent, because potentially the materials can have a massive impact in all the interconnect technology, and so in the energy consumption of our electronics. Still, that was the stability, the mechanical property, but still there was a lot of questions in terms of integration, a lot of questions also in terms of how the dielectric property could vary depending on slight variation of the balance between boron and nitrogen, and so on and so forth. So it turns out that not only Samsung was working on that, but then big players like TSMC in Taiwan and Huawei and Intel are now all working on these materials, try to optimize its property, and not only for interconnect, because it can be also used in order to improve other kind of active device in electronics. But this kind of question, for instance, of computing the dielectric constant of a system that is enormous, gigantic, and disorder is extremely challenging. It's probably the challenge, the forefront frontier of what we can do with computation today. So you can do a simulation with a small unit cell, but that will be not representative of a gigantic model with millions and millions of atoms. So once again, and this is all, kind of in-house, methodologies that can really cope with this gigantic model and compute their property. And then if we set up a workflow in which we have generate the interatomic potential, then we create the structure with the molecular dynamics, and then we go with this methodology, we go into the computation of the dielectric property. This kind of workflow is extremely challenging to do, but only using AI and only using these linear scaling methods, you can give an answer to the industries. Okay, now I want to point out the second level of revolution, the construction of this digital model using advanced STEM microscopy technique, right? TSMC, Intel, and all these big players, they are trying to scale down further the electronics, but they are arriving to some device in which you can almost count the atoms. Okay, there is a dimension which is lateral, we don't see, this is just a cut. But so you have a possibility to capture the structure in 3 dimensions and start to play with that and start to understand what limits the performance, ultimate performance. This is a picture, and you can see a lot in the literature, like this is an Emixin paper where there is a kind of tracking in time as the structure evolves using AI, you track all the structure also change in time under irradiation. So, and then you get some structure with which we can look at this property. So we consider this especially for CVD graphene in the past, because CVD is also very important for a number of high-tech applications in photonics. For instance, we have Black Semiconductor in Europe, which is scaling up the production of graphene and photonic devices. So that's really important. But the problem of a full wafer scale graphene or 300 nanometer is that you have more atoms, carbon atoms, than the galaxies in our known universe, which is actually a huge number. Close to trillion actually. But we can construct this digital twin. This is not a reconstruction from the experiment, but it could be done without any problem. And with this structure, you can also play and try to see all the contamination, further contamination due to the absorption of chemistry, of molecules on top of the grain boundary, which are more reactive, or the impact of a substrate. All of this will eventually affect your metrics, which is if you want to use graphene and having a good sheet resistance, for instance, of the graphene, you would like to know what is the impact of changing the grain size in the polycrystalline morphology, and what is the impact of having a contamination by this or that. Okay, and it turns out that with the technique we have, we could really match, and this is surrounding this orange, exactly the value that is measured experimentally. This was made by some group in China. So what does that mean? That means that thanks to the digital twin and thanks to this kind of simulation, you can set up the target. You can explain, okay, if this is a condition of your materials, and as we see it, if you improve your material in this direction, then you will get this metric or this metric. So you can really have a guidance to the experimental and the innovation process. Okay, there are plenty of, and I don't know exactly what the groups in the Athena networks are doing, but they are probably interested in plenty of different other kind of applications like battery, photovoltaics, and so on, supercaps, so on and so on. So each time you are considering bringing innovative advanced materials, you have a lot of problems and a lot of questions in the optimization. I have discussed a lot of time with Julio Gomez from Avanzare, and he always was telling me we don't know how to further optimize or thermoplastic, for instance. Okay, you put graphene in your plastic to make it more thermally conductive, but you don't really know what is the parameter in order to get the best possible material for a given performance objective, right? And the problem in all the materials, I guess you are studying, and Manos, is that they are extremely complex. They are not super simple, defect-free layer of graphene. So all these materials are very, very complicated. But again, by reconstructing the structure of what you are producing in a digital model and look at this property, it might give you quite a guidance. Let me make this final illustration on something we have been developing in collaboration with TEM expert. We are working on trying to understand and to optimize the technology of semiconducting qubits in order to design quantum computers. Okay, so these are type of qubits, semiconducting qubits based on silicon and germanium, produced in Europe, in Nicebohr, Quantum Foundry, or in Delft, or in Austria. And that is the kind of materials that can be, and the kind of picture that can be extracted from the TM image. So what we are doing now is using pattern recognition and deep learning, we are capable to reconstruct this model in 3D, okay? Having the position, not 100% certainty, but enough certainty to capture, for instance, the roughness at the interface, the compositional disorder, and so on, the impurity, and so on. Having a sense of this. And then with this, we use our methodology in order to look at the property, crossing the interface at the interface, and ultimately our objective is to be able to correlate the structure with the qubit performance in order to further improve the qubit to its maximum possible performance. So you can find, if you're interested, because the kind of generic workflow, we call this end-to-end workflow, from the material production to material characterization to material design or properties simulation, and then material design. So we have this kind of paradigm, which we have explained and detailed in this paper that you can find online. But basically, this technology, this software technology, this concatenation of codes of AI techniques in order to work on the digital model and then to extract the property, it's completely transferable to any type of materials and so of potential relevance for any type of application. So my invitation to Manos and to all of you is to really consider seriously that artificial intelligence will be a game changer for material innovation. And if we don't do it, if we don't, network and work together, we should not be. You should not worry that in a few years, if the Chinese are not yet strongly engaged into that, they will jump and they will finally have their own accelerate their innovation, and we will be scooped again and again. Okay, I don't know how much time do I have? Like 5 minutes?
No, you still have 15 minutes.
Okay, so I can take my time. So I hope the message was quite clear. Now let me also give another example. I think also it's important. I could have put some slide about photovoltaics, the work of Manos and Francesco and Aldo, but I want to say that 10 years ago, or more than 10 years ago, when the flagship was launched, really the main idea was to bring our innovation, our discoveries to application in order to become more competitive, European industry becoming more competitive. So we started to work on many different research track, and Manos has been leading the photovoltaic track with his friends, and okay, fine. At that time, AI was absolutely not in the game. Okay, I was, as was mentioned by George, I was personally privileged and honored to be offered to lead the spintronic work package, thanks to the presence of a Nobel laureate, Albert Fert. And so I have seen, and I will show you what happened in our spintronic and why AI, at the end of the day, became essential to progress. Without AI, no way to do anything else. No need to have more money if we don't bring AI, because we cannot progress further. And I want to show you this, but I will anticipate that advanced battery, functional lightweight component, photovoltaic, flexible consumer, exactly the same problem. Okay, so that would be an illustration of spintronic. You are not expert of spintronic, maybe, but please understand why my narrative is about. It's not about this particular track. It's about the fact to show you that without artificial intelligence, we arrive to a point of no more innovation in the next decade. Okay, so the Albert discovery was French, great scientist. He made a prediction during his PhD. Then several years after, that was confirmed, and this has a massive impact in memory storage, or a lot of things that are now in plenty of high tech, right? And one of the important things is this non-volatile memory. So fantastic! That was a scientific discovery. Unfortunately, the patents were made in the US. So even though in Europe we have the patent, all this technology are now developed in Asia or in the US, and we have been scooped once more. After 10 years of the flagship, of an activity of, let's say, a task force of probably the best European groups, fundamental, also some company joined, and IMEC and so on, we arrived to a final conclusion. Okay, 10 years of work. Are two-dimensional materials really good for improving spintronic technology, which was our mission? So we published this paper in Nature. We engage big players like Samsung and Global Foundry to also have their vision. And basically, in this time and in this review, we were the first in Europe to report the co-integration of a two-dimensional material with really the mainstream materials used in today non-volatile memory technology. And in the fab environment, this was performed by IMEC, and here we have a nice picture where, okay, you cannot probably recognize, but there is a few layers of tungsten disulfide which are encapsulated in a memory stack, which is extremely complicated. But that alone has been a very, very challenging technology step. Okay, so again, there is no such a report in the literature. So Europe has demonstrated that this 2D material, on the paper, they can improve the performance of these materials. And in addition, we had some activity at the end of which we could report on this type of co-integration. The stack was still functioning, and there was some change of the magnetization that was still functioning. However, that was the only, and was at the end of the chain of the flagship, and we could not demonstrate that this material in particular could improve the performance of the memory, because more investments, more time would have been necessary. Okay, so we wrote this kind of roadmap. Okay, we end up of flagship in 2022, 2023. So we kind of extrapolate what would be necessary. And despite the fact that we European were the first to really show a large-scale integration and come to this, and that was involving Graphenea and the Singulus technology and IMEC and all the knowledge we had from the spintronic, basically there was a disruption here. But actually, disruption, as I told you and as I want to point out now, is not only due to the fact that we lack money, but is also due to the enormous complexity in order to be able to single out what is the best materials to achieve the upper performance of this technology. And of course, we can say, okay, and there are plenty of people or friends still in Europe, and even my group, we're still looking at different type of stacking different materials in order to have higher and higher performance. But there is a problem. And maybe ultimately have the ultra compact memory block in which we just have a 2D ferromagnet with a 2D strong spin orbit coupling with graphene and so on. But the problem is the following. As you know, when you start to have two materials in contact, and this has been shown, and the big discovery of superconductivity in bilayer graphene, it's not only the stack that matters, it's also maybe the alignment of the atoms one with respect to another. Okay? So if you take graphene and another 2D materials, or a magnetic material with graphene or with another 2D material, actually the angle will matter. The interaction between the two materials will depend on the symmetries, okay, and also on the nature of the atoms in contact, but also on the symmetries that can vary quite a lot when you change the angle. And so here it's just an illustration. Here we vary a bit angle and we have a gigantic change of the spin transport anisotropy in the material. So we are in a big problem, because even if we find the way to stack materials, and maybe we use robots to do that, that in this kind of paper was nice. I mean, they assemble 80 different two-dimensional materials and kind of controlling a bit the angle, and there are companies that have developed further ways to control the angle. That's fine. The problem is that the number of possibilities is just impossible to tackle with current methodologies. Okay, if you take just four different layers and you to stack them, and you want to get the best, you will get 40 billions of possibilities. So how can you simulate 40 billions of possibility with DFT? How can you create 40 billions of possibility to find the best? And there is certainly a manner to get the best possible alignment, and in order to tailor all the property, even for a photovoltaic cell or whatever. But this seems to be completely out of reach. Okay, so that's kind of AI is coming in. We make the math, and we realize that with our capability of computational capability, without AI, let's say, it will take us 1,000 years of computation in order to explore, let's say, a portfolio of 100 or millions of possibilities. 1,000 years. So it's just not possible. I cannot live for 1,000 years, and Manos, I don't think he will live for maybe a bit more, because in Greece he's more happier. But 1,000 years is just impossible. But by intercalating AI in all the process of a workflow, we reduce 1,000 years in 2 years. Okay, so it means that something that seems impossible, AI make it possible. You bring it in a workflow, you will screen massively, you will optimize, and you will understand you don't need to tune all the, oh no, you need to make this. So the on the way, on the fly, AI will learn how to go into and to reach the metrics you are targeting. And that's unique of artificial intelligence. And the fact that the methodology are not so realistic, you can anticipate that you might achieve and provide to the technology, so the engineer, the proper recipe, like an alchemist, for this technology to reach its highest possible performance. Okay, so I hope I convince you that we are facing a new epoch, a new area where artificial intelligence will boost and revolutionize the way we develop innovation for innovative advanced materials. I like to point out that there is a conference where it's very recommended to you if you really are interested in that and really want to know what is going on. Come to this conference or look at the speakers and look at the abstract that will be released. Actually, in addition, it is a nice place. But this conference is a symptom that the community is growing, and that artificial intelligence is coming to play a big role in our daily life of a researcher, either we are in Heraklion or in Barcelona or wherever else. Okay, so with that, I think I have to stop, and thank you very much for the invitation for a question. Thank
Thank you
you.
very much, Professor Roche, for this very enriching and entertaining presentation regarding different topics on materials and AI. So I would like to give the floor now to the audience for the Q&A. So first one is Leandro. He's one of our eminent students. Please, Leandro, you have the floor.
Okay. Good morning, Professor George, Stephan. First, thank you for your talk. It was very interesting, and I have some questions because this is kind of some fit. Well, can you hear me well?
Very well.
Okay. So this
Yes.
is a field I am actually very interested. So first, my first question is like, aren't you afraid, or how do you manage the feeling that maybe if AI advances like enough, you will require like less researchers doing like research in optimization and materials and that kind of things?
Question. Then there is a second question, so I answer the first. Right, first. Okay. Look, my group. I don't think so. I take my group. My group, since we start to collaborate with Samsung, has increased because we got contract from the industry. And from maybe 5, 6 people, now we are 15 people in my group. And now I'm launching a spin-off on AI for material design. So in order to use this workflow, and in this spin-off will develop workflow for whatever application, for research group, companies, and provide this technology so that the company or the research group can use it, user-friendly interface, and can use it like very efficiently. But in order to use and to develop this kind of technology, you need to know the physics. You need to know, and then if you want to apply to chemistry, you need to know very well the chemistry. You cannot be a complete ignorance. So it means that students who actually in a lot of different master are taught about machine learning technique in many different masters. Student will have two possibilities, let's say. Either they continue to work in research group, the student interested in simulation and AI and stuff, in research group that probably in time will more and more interact with plenty of companies, or either they will, after a PhD, they will move to the company, because even in the company, you will need to have expertise, a physicist or mathematician or chemist or biologist to be in this company to guide the further development or the connection, the commercial contact with other kind of fields and so on and so forth. So I don't feel a problem. I have people in my group doing also quite fundamental research, and they are all using ChatGPT to check the code. The things that it does, it accelerates everything. And the second thing is that if you don't use it, then you will be scooped again and again because your competitors sooner or later will use it. And if you, for instance, you're just using simple DFT to do simulation or whatever, you will be scooped all the time and your paper will be rejected all the time. So there is no way out. You have to jump in because this is a tool like when people use a computer and people use, no, just computing by hand. You cannot compete. So I don't think it causes a problem. And from my perspective, maybe I don't see all the problems of the world, right? But from my perspective, it's just like a knowledge that is necessary. And the fact that, for instance, in Australia, we will develop a technology that is user-friendly for experimentalists or for engineers makes that you, who has no need to be an expert in DFT, an expert in MD, an expert in large-scale computational, you will be able to use this workflow to tune some parameters, to see the result, like a kind of using STM or X-ray diffraction or a kind of electrical measurements equipment. So what we will bring with our company, which is to be launched in a month, kind of a month scale, is to provide a tool for you in a week to become, trained enough to use this for testing your own questions.
Thank you. I do have several more questions, and now these are, I'm sorry if it will take some time. These are a little bit more technical. I would like to know what's kind of tools like the computational algorithms. What tools do you use to make them? Like Python, TensorFlow, PyTorch, or yeah.
You say all of them. PyTorch, yeah, we use this method, especially PyTorch. I mean, for our current research, we are using this type of tools, open source and so on.
Okay. And now, important one, like when you make these digital twins, what kind of parameters do you use to measure like the accuracy of your models? Because, for example, I have worked with image classification. So basically, in there, the accuracy is I have a label and I count like the number of labels that it was identified correctly. But in your case, in this kind of digital twins and materials, when you're analyzing the properties, what's the thing that you are actually measuring as the accuracy of your system compared to, let's say, the real world materials?
Good question. So may I invite you to have a look at the archive paper, okay? Because that I have in my presentation, so you can check. Here we have a lot of technical details about how do we reconstruct the digital models from TM image and additional spectroscopic technique, because we also identify a position of germanium versus silicium. So that's very important. The composition, the chemical composition is an important part of the digital model. Then, of course, at the moment, our workflow does not provide a one-to-one connection between the morphology, the atomistic morphology, and the qubit performance. We have submitted a big project to develop this because this is extremely challenging, right? But what we can compute at the moment is just to evaluate the degradation of the electronic property, the electron bond profile, and things based on a given morphology that is producing the material. So I don't know if I respond fully to your
Yeah,
question, but
no. I think, yeah, it kind of gives me like an idea. It's more like going into the degradation of the material, like, as you mentioned, and like the performance. Okay, and
yeah.
just one last question, but this one is very, very personal. It's like non-technical at all, and it comes from a place like of respect and kind of admiration. Let's say if in the future, because right now I am in my first years of my master. Let's say if in the future I am interested in working in the ICN2, maybe for my master thesis or maybe after my master, like the time I'm planning is maybe 1 year from now, more or less, which is what I'm interested in. What would you advise me, or what do you recommend, or what kind of pathway should I take for to work with you?
No, just send me motivation and your CV. I mean, that's I expect we will grow. I mean, if you're interested in computation and in AI and stuff like that, I expect we will grow because part of the of our current team will move to the company sooner or later. So yes, we will need people. And not only us,
Thank you.
there are plenty at the European level, as Mano said, the IMI. There are plenty of other companies doing simulation, and there will be a lot of European project. And I hope we will have one with Manos, where my company can work with Manos laboratory. So we will also need people in Manos lab who know a little bit about AI and can then use, for instance, the workflow that we will develop for Manos. So it's not only coming to us; it will be coming also working in any kind of labs and be aware of this kind of new techniques, and then say to your boss if he is not aware that that might be a game changer for his research.
Thank you so much. Thank you.
Welcome.
Thank you, Leandro, for your contribution, and also Professor for the feedback. I'm very happy that our students have very big goals and they want to progress their career. So we will help them definitely. Then I would like to give the floor to another eminent student. Hassan, I think, was first raising the hand. So please, Hassan.
Okay. Thank you, Professor. Can you hear me?
Yes.
Okay. Thank you, Dr. Stephan Roche, for your eloquent presentation. It was really intriguing. So I have a question about your workflow. As I have seen, you haven't gotten into the details of how the models actually work. You basically presented an overview. So, but you mentioned some keywords like you want something based on DFT probably. So what I'm asking, like most of the machine learning models are basically feeding the data, training the model, and then getting the output and comparing it with the experimental data. So is there any plan to include any reasoning model inside your machine learning model so that actually the decisions that they are taking, it has some logical basis rather than just parroting what they have learned previously?
That's a good question. Yeah, at the moment, I'm not sure to really understand what the reasoning, what you say about the reasoning. But at the moment, indeed, we are trained or machine learning on a DFT database, right? So there is a big question: is your database, big enough and having all the physics in order to then have some meaningful machine learning potential, right? And this we have seen that. I mean, if you have a structure like a multi-layer of disorder materials which can interact with some van der Waals force, you need to have into your training sample, the proper initial small unit cell which can capture this essential physical mechanism. So that's why there is a big there is a serious initial intellectual reasoning about what is the physics of your materials and what is the training sample that you have to generate. Okay, and once you have that, well, you have your training, you have your machine learning potential, and then of course you can introduce into molecular dynamics and go into the thermal, mechanical, and so on, stability, and so on. Then, of course, as you said, the validation with experiments is very important. The point is that if you don't have reconstruct a digital model, that's what all I explained, and if you don't know what is in your experiments, in your materials that you've grown, you might be, contradicting, because there might be some contamination in your materials that you have not taken into account in your database, right? So it's a bit tricky. It will be necessary to do a kind of systematic comparison between your initial guess of the material structure and its contamination and the reality of the material. So I don't know if when you say reasoning, what do you have in mind? If this is something that can help in this design, or maybe you can be more precise. That could help me actually to understand what you have in mind.
Okay,
If I
okay.
didn't answer.
Basically, I meant like physics model, like do. Okay, okay.
Yeah, it's a physics models, but again, I wanted to point out that uh, this cycle with an experimental activity will be very important to be sure that then the AI models can be used like in a kind of a pilot line, right? We have to really first secure that the realism is double checked with a systematic one-to-one comparison with experimental data.
Yeah. I have a really short question for the second one. I have already looked at this AI for AM conference that you have, like in the last presentation. Like, is it, and I have seen that the fees for students exhibitors is around 300. Is it possible for the students of this eminent group to like reduce a little bit so that we get more participants to join it? I mean, you may
If you are
consider
not, yeah, if you are all PhD student or you're a master, I'm not sure.
masters.
So if you are a master student, what I will suggest to Manos, I mean whoever is the coordinator of Athena, is to discuss with Antonio Correa, and certainly a deal can be made because we used to in this conference for master student that comes just to participate, they do not present a poster or they do not present an oral, but oral is too late now. But if it's just attending, we used to reduce their fee, okay? And for instance, yeah, we cut the conference dinner, and so it can go much lower. But that's a kind of maybe either you do it a one-to-one, you contact me, and or either you ask to you, the coordinator of Athena, if there are more candidates, we can set up a rule so that your cost will be at minimum. But it will not be zero, but it will be much lower.
Thank you. Thank you very much.
Thank you, Hassan, for the questions, and thank you, Professor, for the feedback. And then I would like to give the floor to another student from Eminent, Ahmed. Yes, please.
First of all, hello, Professor. Thank you very much for your presentation. I just, at the beginning, you said that the cost and the energy increases with time with the more the models get advanced and the amount of GPUs that we use in order to train the models. But is it possible that that it could be cheaper in the future, that it might not take as much energy and as much cost with when it's getting developed? Like for an example, there's DeepSeek people that the Chinese counterparts that try to do, they in their technical report, they, at least in the V3, I don't know about the new R11, but in the V3 they have used like not a lot of GPUs and old GPUs compared to the one only released in the US. So is it that possible that with time we can actually decrease the cost and the energy consumption similar to the way, or maybe the Chinese weren't that honest about the number of GPUs and the actual cost that they used in
Good question.
in manufacture or the development of their language model, let's say.
Yeah. So good question. The problem of the energy of all this infrastructure is really is a real problem. Microsoft, for instance, is already, I'm not sure if this decided, but they're already thinking of buying or a nuclear plant for their infrastructure. So AI is not, it will always have a cost. Okay, because even what they did use DeepSeek, they used a former NVIDIA infrastructure, not the top of the top,
The H800,
but
yes.
yeah, exactly. But they train a model for doing kind of they just check some very simple task, okay, kind of metrics to compare with OpenAI. But they didn't train the model to do something extraordinary, right? When you will have to, for instance, in what I have shown of the Amorphous boron I tried, we had to use a lot of resource in high PC supercomputer, right? So anytime you will have to look at a particular material, let's say what Manos is doing, like the kind of assembly of perovskite and 2D materials and something like that. Anytime you want to change a material, you will have to redo the calculation, the DFT, training sample, the machine learning, and so on. And this will have a cost. This is expensive on supercomputer. You cannot do this on the laptop. So if you want to explore thousands or many possibility, you will have to multiply, and the resources will be limited and scarce. So the faster you can use and you can train your AI, the better, and with the less energy possible. But I think that even if the Chinese can demonstrate something and that would perform the computational cost of OpenAI, it's just what they have demonstrated is unpractical. It's not for use, right? It's just like a kind of specific metrics. Then when you want to use this massively for innovation in all the industry sectors, we will need a huge amount of computing resources, and you will need a very efficient AI algorithm and so on and so forth. So we will not, if we still use the current hardware infrastructure and hardware technology, we are facing the problem I have mentioned in my talk. So discovering new materials that can help to develop new hardware, much less energy, consuming, is an important direction for innovation.
Thank you very much. Just last question. So basically, most of us are in their first semester of the masters, and we still have like nearly 1.5 years till our thesis. What topics or building stones should we learn about or study to or have really good knowledge of if you wanted to get into the AI field by the end of our studies, to have, like you told us, you mentioned PyTorch, you went Python. What other key knowledge that you would look for in a candidate at the end if you would like to supervise him in a research?
All the machine learning technique, I mean deep learning, all this is coming into the educational program, so that's highly recommended. Also practicing and using this large language model, and learning them a lot. I mean, of course, it's ChatGPT, but you can try others. And I think there are plenty of things to learn or to use them efficiently and so on. Even the free version, of course, there's the commercial version also. Just a note about DeepSeek. If you use DeepSeek and you do something online, everything you do is copied, and they know what you are doing.
Yes, I've seen it.
Yes. Okay, so it's preferential not to do something online if it's something a bit confidential.
All the packets are sent to China. Somebody tested it using Wireshark, and it showed that all the packets were sent to Beijing or to servers actually hold supervised by Alibaba, which is actually in China as well. So to not mention any confidential information or something personal about you on those stuff. So
the problem is when you use this kind of large language model, you ask questions, and sometimes all the information in the good question that has been asked, and this is science is also asking the good questions, and the answers are important, of course, but you can ask plenty of stupid questions. But if you ask good questions, and if the software is capable of identifying good questions, then you lose some information. That's why in our spin-off, actually, we develop workflows offline for the companies, because then they can use completely disconnected from any spying process.
Thank you very much. Just lastly,
for the question, and Professor for the nice discussion about this topic. And then I would like to give the floor to my colleague, Professor George Kavoulakis from HMU.
Yeah, hello. First of all, wonderful presentation. Thanks a lot. There is something, first of all, I'm not familiar with AI, but I wanted to ask you, over the years, we have developed all these sophisticated techniques like density functional theory that you mentioned, Monte Carlo, numerical diagonalization of the many-body Hamiltonian, other mean field methods. So it is not clear to me how would AI, would it make use of these techniques? What is it, the basic idea that you have in your mind?
Good. Of course, the property of materials can be very complex depending on the situation. Low temperature, you change the temperature, the system becomes more strongly correlated, and so on and so forth. So, actually, all the available, I just say a bit about our company that is about to be launched, is a way to connect with all. I mean, having all this open source software is good. The problem is easy the use. I mean, their training to this model is sometimes complicated, and then you have to update the compiler, the library, and so on and so forth. So basically, our company will make things much easier. And if you are developing a special tool, let's say special code, our company will offer you to partner and to branch your code into our workflows, and then to participate into the benefit when the people will use it. So basically, that could be also a way to enlarge the use of some methodology that people do not master well, but if properly integrated in a user-friendly interface, then it will be more of use for a larger number of people. And of course, that's again a question of knowing when do you have to use these methods for a specific problem. So you need to know the physics of physical phenomena, and to know that when DFT is not appropriate, and you have to go beyond DFT, GW, or TDDFT, or other kind of approach. So definitely understanding well the DFT methods and their limitation is extremely important. And concerning all the existing DFT model, they will have their use in the future kind of workflows where AI will accelerate the innovation and the realism of the simulation.
Okay, thanks a lot.
Thanks a lot, George, for the question, and Professor for the feedback. And let me check the chat because, okay, I can see a comment from our student, Christina. Thank you for the presentation. My question, you said AI reduces calculation time by a factor of 500. What do you compare with? Machine learning?
Yeah, no. So we compare. We did the following exercise. We say we want to simulate, let's say, 100,000 of different combination of 2D materials, simulate their property, and we just make the math about maybe it was 1,000,000. I don't remember exactly, 100,000, 1,000,000, a different configuration, and we compute the time, the computation time it takes to make the calculation, to design the model, and then to run the calculation, and so on. We just compute the time, okay? And then with the methods we have without AI, and then we bring AI, which is an accelerator inside the workflow, and then we just remake the calculation, and we found this factor of acceleration. So it's just like without AI or AI simulating a huge number of possible materials. Okay, I hope this is clear now.
Thank you, Christina, for the question, and Professor for the feedback. And let me check the chat. I don't see one. May I have one question as well, please?
Sure.
I saw in one of your transparencies, you mentioned about the seat resistance of graphene. I guess this was for the CVD graphene, right?
Yes.
And you mentioned with the calculation, you can reach approximately 10 ohm per square, etc. I would like to know what is the doping level you are using for this calculation? Because I guess this is important.
Yeah.
You consider,
Sure.
I mean, undoped CVD graphene, it has very high seat resistance, like 6,000
Sure.
ohms.
Yeah, sure. We actually, yeah, this is in the paper. I don't exactly remember. We probably used a doping level that was typical. We also compare with the experiments. Let me show it again. I don't know if you see the slide again.
Yeah, we can see the slide.
So yeah, okay. So this is a measurement that have been made by one Siren group, in which we try to be in the same condition, I would say. But you're right. I mean, of course, you change the doping, the sheet resistance is also modulated a bit. Okay, so
I
I
agree with you that the grain size affects a lot, the steepness of the resistivity versus voltage curve in the regarding seat resistance drop. But yeah, it might be interesting to check this paper. Okay. Thanks a
Good.
lot.
But contact me again if you have you want to further discuss this. We'll be happy to discuss.
Under the microphone. Okay. Thanks a lot for this for the feedback. And then any final remarks, Manos or George, anyone?
We'd like to thank again Stephan for this nice talk and the inspiration he gave to our students. Honored to be friend and hopefully collaborator in the next proposals, as you said.
We do, Manos, we do.
Yeah. Looking forward for your company.
Yeah. Thank you, Manos.
Excellent.
Keep in touch.
So, once again, we would like to thank the contribution of our speaker, Professor Stephan Roche. It was a great pleasure to having you and learn from you. And before we close today's session, I would like to announce the next session, which is going to be delivered by Professor Alexandros Jallas from the University of Ioannina in Greece, and a related topic again with AI, but this time mostly on healthcare and clinical applications. So once again, thanks everyone for your participation, our students for the contribution, and everyone else joining. And up to next week, take care and see you. Bye-bye.
Bye, George.
Bye-bye.